welcome you all in this lecture. Today I am going to discuss the expansion of function of several variables. First I will discuss the expansion of Taylor series and Maclaurin series for a function of one variable, and then we will expand this theorem for function of two variables. Taylor series for function of one variable. Suppose that let fx be a function of x having continuous derivatives in the interval say a plus h, and assuming that it can be expanded infinitely, then the Taylor series of the function fx is given by your fx plus h equal to fx plus h f dash x plus h square upon factorial to f double dash x, and your nth term will be h power n upon factorial n fn x, as we assume that it can be expanded for infinite. So the Taylor's expansion of a function fx is equal to this one. Now let us assume that h equal to, say, let us put our, say this is your fa plus h, so we will have fa here, and this will be your fa and f double dash a, and then we will have fn a. So let us put that h equal to x minus a. Then now if you replace your h by x minus a, then you can say that your fx is equal to fa plus x minus a f dash a, then we have x minus a whole square upon factorial 2 f double dash a, then x minus a power n upon factorial n f n a. So these two series are equivalent to each other. This one is Taylor's expansion of fx in powers of x minus a. This is your in powers of h. We can also write this series, say it is series 1. We can also write it, you can also write 1 in powers of x. You can assume a equal to 0. Now if your a is 0, then this will be your f0 plus x f dash 0 plus x square upon factorial 2 f double dash 0, and so on. So if our a is 0, that means when we expand the function fx in the interval 0 comma h, or if we assume h as x, then this series 2 is known as Maclaurin series. So if a equal to 0, then your fx equal to f0 plus x f dash 0 plus x square upon factorial 2 f double dash 0 plus x minus x power n upon factorial n, the nth derivative at 0 is known as, this is known as Maclaurin series. So this is your Maclaurin series, and this fa plus h equal to this one is your Taylor expansion of a function fx. Maclaurin series is very important because we can expand any function in ascending power of x. For example, we can have the series for sin x, we can have a series for cos x, we can expand each power x into cos x, we can expand log 1 plus x, we can expand each power tan inverse x, we can expand tan inverse x, tan x. So this one is very important because we can have series for many functions. So let us find out the series. Let us expand your sin x and log 1 plus x in powers of x. So solution, let fx equal to sin x. Then your f dash x is cos x. F double dash x will be minus sin x. F double dash x is minus cos x. F4 will be your again sin x. Now from here your f0 will be sin 0, which is 0. F dash 0 will be cos 0, cos 0 is 1. F double dash 0 will be minus sin 0, which is your 0. F triple dash 0 is minus 1. F4 0 is 0. And then the fifth derivative will be cos x, and the fifth derivative at 0 will be 1. And similarly we can have other derivatives. So let us put these values here. Hence, therefore, our fx equal to f0 plus x f dash 0 plus x square upon factorial to f double dash 0. Then the third term, the third derivative. Then we can have the fourth one. Then the fifth, and so on. Now we have assumed that fx is sin x, so in the left hand side we will have sin x. Now in the right hand side, the first term is f0, which is your 0. So that means your sin 0 is 0. So the first term will be x into f dash 0, which is your 1. So we have x. Your double derivative is 0. Triple derivative is minus 1. So we will have x minus x cube upon factorial 3. Then the fifth term is 1. So the expansion of sin x is this one. Sin x equal to x minus x cube upon factorial 3 plus x power 5 upon factorial 5. And similarly we can expand this term log 1 plus x, because this second part, let us assume fx equal to log 1 plus x. Then your f dash x will be differentiation of log x will be 1 upon 1 plus x. F double dash x will be minus 1 upon 1 plus x square. Then f triple dash x will be, this will be your minus 2, so this will become plus 2 upon 1 plus x whole cube, and so on. So from here your f0 will be, you can see that it is 0, f dash 0 is 1, f double dash 0 will be minus 1, f triple dash 0 is plus 2. So your Maclaurin series will be, so from here you can see that your Maclaurin series is equal to, so your Maclaurin series will be now f0. f0 is 0, so the first term is 0. So in the left hand side, fx is your log 1 plus x. Then we have x. Your double derivative is minus 1, so the next term will be x minus x square upon 2. Then your third order derivative is 2, so this will be your 2 divided by 6, so this will be your 3. So the expression of log 1 plus x is x minus x square by 2 plus x cube by 3 minus x power 4 upon 4, and so on. So this is the expansion of log 1 plus x. Similarly we can expand tan inverse x, tan x, and other trigonometric functions. Now let us solve a question based on this Taylor series. So expand, say sin x in powers of x minus a. So solution, your Taylor series is, as we have to expand in powers of x minus a, and for powers of x minus a we have this series. So our fx is equal to sin x. So your f dash x will be cos x, f double dash x will be minus sin x. So your f of a will be sin a, f dash a will be cos a. Let us assume a as pi by 2, or you can say, you can assume any other value. I am assuming a as pi by 4, so that we can have some particular value. Now you can see that your sin pi by 4 is 1 by root 2, cos 1 by 4 is again 1 by root 2. This will be your minus 1 by root 2, and we can find other values. So therefore your fx will be f of a plus x minus a f dash a plus x minus a whole square from factorial 2 f double dash a, and so on. So f of a, let us assume a equal to pi by 4. So the first term is 1 by root 2, then we have x minus 1 pi by 4 into f dash a. Your f dash a is 1 by root 2 plus x minus a is your pi by 4 whole square from factorial 2, then your f double dash is minus 1 by root 2, and so on. So this is the expansion of your sin x in powers of x minus pi by 4. The next question, next, show that f of mx is equal to f of x plus m minus 1 x f dash x, then we can have m minus 1 whole square from factorial 2 x square f double dash x, and so on. Let us prove this result where m is your any number which can be a positive or negative. So solution. Now this mx can be written as x plus mx minus x. So we can write it as x plus m minus 1 into x. So this is like f of x plus h. Now for the expansion of f of x plus h, we have this Taylor series, which says that it is equal to f a plus h f dash a plus h square from factorial 2 f double dash a, and so on. So let us use this Taylor series. So this is equal to f of x plus h. Now in place of h we have this m minus 1 x. So this is equal to fx plus h into f dash x, then h square by factorial 2 f double dash x, and so on. So this is your answer of this problem. Now expand square root of 1 plus x plus 2x square in powers of x minus 1. Let us expand this problem in powers of x minus 1. So solution. Here we can write this term as, let us make this one as a perfect square in powers of x minus 1. So we will have 2x minus 1 whole square. That means this is your 2x square. So we have this term. And then the second term will be your x square plus 1 minus 2x. So let us show, that means this is your 2 times x square plus 1 minus 2x. So you can say that we have added 2 here. So let us subtract 2. Then this is your minus 4x. So let us add 4x. Then we have these two terms, 1 plus x. We can also write this term as like this. Now this is equal to 2x minus 1 whole square. Now this is your 5x. This is your 5x, and we can write it as 5x minus 1. So we have 5x minus 5. But here we have minus 1. So we can write it as plus 4. Now you can see that this is your 5x minus 4, 5x minus 5 plus 4. And that will be your 5x minus 5 plus 4 means 5x minus 1. This is equal to 5x minus 1. So we have this term. Now if we assume fx equal to square root of x, then your f dash x will be 1 by 2 root x, and your f double dash x will be, the differentiation of x for minus half will be minus half into x for minus 3 by 2. And we can write it as 1 by 2. So this will become your 1 by 4 into x root x. Now suppose that this is your h. Now let us assume this one as h and this one as x. So we can see that this is your f of x plus h. That means f of x plus h, and for f of x plus h we have this formula. So let x equal to 4 and your h equal to 2 x minus 1 whole square plus 5x minus 1. Then your fx plus h will be equal to, now your fx was square root x, so this fx plus h will be square root of x plus h, and for this your x is 4, your h is this one, and this is same as square root of 1 plus x plus 2x square. Now with the help of Taylor's expansion we can expand this term. So this is equal to fx into h f dash x plus x square upon factorial 2 f double dash x and so on. So your fx means f4 because our x is 4. So the first term will be f4 plus h is this one. Then we will have f dash, this is your h. Then we have f dash 4. Then the next term will be the whole square of this one divided by factorial 2 into f double dash 4, and then remaining terms. Now your f4, if we put x equal to 4 here, then this will be your 2. So the first term is 2. Then 2x minus 1 whole square plus 5x minus 1 and into f dash 4. Now this f dash 4 will be, let us put x equal to 4. So this will be your 2 and we have 2 already. So this will be a 1 by 4. So the next term will be 2x minus 1 whole square plus 5x minus 1 into 1 by 4. Then the third term will be 2x minus 1 whole square plus 5x minus 1 divided by factorial 2 and whole square is here. Then f double dash 4. Let us put x equal to 4 here. We have minus sign here. So if we put x equal to 4, then this will be 16 into 2, that means 1 by 32. So here we have minus 1 by 32 and so on. Now if you simplify this term, on simplifying, so if you square this term, then this will be a power 4 and here we get power 2 and this power 2 and this power 2 will get merged. So this is equal to, so this series is equal to 2 plus 5 by 4 x minus 1, then we will have 7.64 x minus 1 whole square and then so on. You can see that here we have 5 by 4, 2 plus 5 by 4 x minus 1. Now if you merge these two terms, this one and this one, then we will get this coefficient and so on. The last question based on this series for function of one variable is let us expand question. Expand log 1 plus, say log 1 plus under 1 plus x square in powers of x and find its general term. And we have to find out its general term. General term is your nth derivative at x equal to 0. So here we have to find out the nth derivative of this function. So we will use our Leibniz theorem to find out this nth differentiation. So let us differentiate this one first. directly with respect to x, then we will differentiate with this again. We will differentiate it with respect to x. So after two time differentiation, we will use the Leibniz rule, and then with the help of Leibniz theorem, we will get our yn 0 or fn 0. So this fn 0 will be your general term. So solution, your y equal to log 1 plus under 1 plus x square. So your y1 will be, that means the first derivative will be 1 plus under 1 plus x square. Then here we will have x upon under 1 plus x square. I think we have done some mistake here. We have x here. This is your x, not 1. So this is your x. So here we have x, and this will be your 1 plus x upon under 1 plus x square. On taking LCM, we will get, now this one will get cancelled, so we will have under 1 plus 1 upon under 1 plus x square. Okay. Now on cross multiplication, we will get 1 plus x square into y1 square equal to 1. So again differentiating. So if you differentiate, then we will get, here we will get the differentiation of y1 square will be 2y1 into y2 plus 2x into y1 square equal to 0. Let us divide the whole equation by 2y1. So we have 1 plus x square y2 plus xy1 equal to 0. So we have this equation. Let us assume this one as 1, this one as 2. Say this is equation number 3. Now let us apply the Leibniz rule of differentiation. By Leibniz rule, we have, I am writing it directly, so we will have 1 plus x square yn plus 2, then the next term will be n into 2x into yn plus 1, then we will have n into n minus 1 upon 2 into 2 into yn, then the next term will be x into yn plus 1 plus n into yn equal to 0. So from here we will have 1 plus x square yn plus 2 plus 2n plus 1 x yn plus 1, then this will be your n square minus n, so we have n square yn equal to 0. So let us put x equal to 0 here because we need the nth derivative at x equal to 0. So put x equal to 0. So if we put x equal to 0, then we will get yn plus 2 at 0 equal to minus n square yn at x equal to 0. Now if you replace n by n minus 2, then we will get this term. Now from here we can have the values of y4, y6, y8 and y3, y5, y7. Now from here by, say, let us assume this one is equation number 4. By 1, 2 and 3. If you put x equal to 0 there, then you can say that from here if you put x equal to 0, then this will be your log 0. This will be your log 0 plus 1. That means we have log 1. Log 1 is 0, so this is your 0. From here we will have y1 0 equal to 1. Then from the equation number 3 we will have y2 0. If you put x equal to 0 here, then this is your 0. So y2 0 is 0. Now from here we can have n is greater than or equal to 2. Now if you find y2 0 here, then on putting n equal to 2 we will get 2 minus 2, so this will be a 0. So now thus we have y3 0 equal to, put n equal to 3 here, so we will have minus 1 square into y1 0. Our y1 0 was 1, so this is your minus 1 square into 1. Your y4 0 will be minus 2 square into y2 0, and as our y2 0 is 0, so our y4 is 0. Similarly, we will have y6, y8 and the even terms as 0. Therefore, we can say that yn is 0 for n even. Now, if your n is even, then we will say that our yn 0 is 0. Now, if n is odd, then let us compute y50. Now, for y50, we will put n equal to 5 here. So, this will be your minus 3 square. Then your y30 was minus 1 square into 1. So, therefore, if n is odd, your yn 0 will be, the last term is, if your n is here, then we are getting n minus 2 here. So, that means your yn 0 will be minus n minus 2 whole square. Then we will have n minus 4 and so on. The last terms are minus 3 square, minus 1 square, minus 1. This is when your n is odd. This is your y50. For y70, we will put n equal to 7 here. So, this will be minus 5 square into y50. So, we will get minus 5 square, minus 3 square, minus 1 square plus into 1. So, in general, your last term is this one. This is our last term. So, our yn 0 will be minus n minus 2 whole square into n minus 4 whole square into n minus 6 whole square and so on. The last terms are this one. So, this is equal to minus 1 to power n minus 1 by 2. Then we will have n minus 2 whole square, n minus 4 whole square into 3 square into 1 square 1. So, if your n is odd, then we will have minus 1 power n by 2, n minus 1 by 2. N minus 1 by 2 is because the first term do not contain the minus sign. So, we will have n minus 1 by 2. So, this is your general term in the Maclaurin series. Now, let us expand in Maclaurin series. Therefore, our fx will be f0 plus x, f dash 0 plus x square upon factorial 2, f double dash 0, and then we will have x power n upon factorial n, fn 0. Now, if you write fx as y, or we can write it as yx equal to y0 plus x, y1 0 plus x square upon factorial 2, y2 0 plus x power n upon factorial n, yn 0. Now, your y0, your y0 was log 0 and log 1 was 0, so this is your 0. X into y1 0. Our y1 0 was 1, so the first term is x. Then the next term is x square upon 2 factorial 2 into y2 0. y2 0 was 0, so the even terms are 0. Then x cube upon factorial 3, y3 0. Your y3 0 is minus 1, so the third term will be minus x cube upon factorial 3. Then the fifth term will be x power 5 upon factorial 5, y50. Your y50 is this one. Minus minus plus, so we have 9. Then the general term is x power n upon factorial n. Then yn 0 when n is odd. So, if you put n equal to, if n is odd, then we can write it as y2n minus 1 0. Now, if n is 2n minus 1, then this will be your n. If you put n equal to 2n minus 1, so this is your 2n minus 2 divided by 2. So, we will have n minus 1. Now, this is your 2n minus 1, so 2n minus 3 whole square. Then at the end we will have 3 square 1 square 1. So, here we will have 2n minus 1 factorial, then your yn 0. Yn 0 means your y 2n minus 1 0, because our event terms are 0, and where your y 2n minus 0 is this one. So, this is your general term, and this is the extension of this log x plus under 1 plus x square. Now, let us move towards the Taylor series of function of two variables. Now, we will prove the Taylor extension for function of two variables. show Taylor series for function of two variable. I am starting with the Taylor series of function of one variable, and then let us try to expand that series. So our Taylor series for function of one variable was fx plus h equal to fx plus h f dash x plus x square by factor 2 f double dash x and so on. This was our Taylor series for function of one variable, assuming that the function has continuous derivatives in the interval x comma x plus h. Now from here we can write it as, now let us take this y plus k as constant. If this y plus k is constant, then using this series, now using this series, that means using the Taylor series for function of one variable, let us expand this series. Let us expand this left hand side, assuming that this y plus k is constant. So this will be your simply f of x, and your y plus k is constant, so just write it. Then your next one will be h into f dash x. F dash x means, now because we have two variables x and y, so this f dash x means del by del x of f. Now your f is x comma y plus k. Then the next one will be h square upon factorial 2, the double derivative of f x comma y plus k, and so on. So this is the expansion of x plus h comma y plus k for function of two variable. Again, this is your Taylor expansion for the function x y f of x comma y plus k. Now, so this is equation number 2. Again, by Taylor series, your f of x comma y plus k is equal to f of x. Here you can see that I am expanding this. Let us take x as constant and expand f of y plus k in powers of y. In powers of k. So we will get f of xy, then k, then the next one will be, you assume, take this term, del f of 1, del y. Then in the bracket we will have f of xy, then we will have k square upon factorial 2, del 2 f of 1, del y2, and here we will have x comma y, and so on. So we have this extension for f x comma y plus k, assuming your x is constant. So if your x is constant, then here we will have just f of y, and as our x is constant, so we will get f of x comma y, then k times, because we have the increment k, so we will have k times the differentiation with respect to y. So we will get del f of 1 del y, then in the bracket we will have x comma y, and so on. Now let us put the value of x comma y plus k in equation number 2. Put f of x comma y plus k in equation 2. So we get, if we put these values here in equation number 1, then we will get f of x plus h comma y plus k equal to, the first term is your fx comma y plus k. So this is equal to simply f of x comma y plus k into del f upon del y, assuming that f is a function of x and y. Then we will have k square upon factorial 2, del 2 f upon del x2, del 2 f upon del y2. Then the second term was h into del by del x of this bracket. So h into the first order derivative with respect to x of this bracket. Then and so on. Then we will have the third term. The third term is x square upon factorial 2. It's double differentiation with respect to x. and so. Now let us then finally next one will be the third derivative with respect to x and so on. So this is equal to, now let us collect our terms. The first term is equal to f of xy. Then the first order term, if you multiply by this, if you differentiate this f with respect to x, then this will be your h into del f upon del x. So we have this h into del f upon del x. Then from here we have k into del f upon del y. So this is your second term. Then the third term, that means this is your terms of order 1. Then let us find out the terms of order 2. Now for order 2 we will have h square upon factorial 2, or we will have 1 upon factorial 2. Then in the bracket here you can see that this is your h square del 2 upon del x2. So we have already taken factorial 2 common, so we will have del 2 f upon del x2 h square into del 2 f upon del x2 here. Then from here you can see that this is your factorial k square del 2 f upon del y2. Then this term, this is your h into k. Then differentiation of del f upon del y with respect to x. So this will be your del 2 f upon del x del y. As we have taken 1 by 2 common, so this will be your 2 times h into k, then del 2 f upon del x del y. So we have these 3 terms of order 2. Now you can find out the terms of order 3. For that we will have to write the next term here. Now this is your one term is this one, which is of order 2, order 3. Then here we have a term of order 3, and we can get another term of order 3 from here. So and so. So the Taylor series for function of 2 variables, thus Taylor expansion for function of 2 variables is f of x plus h comma y plus k is equal to f of x comma y plus h del f upon del x. Please note that here I am writing this series at x comma y. So next term will be k del f upon del y. Then the next term will be h square upon 1 upon factorial 2 h square del 2 upon del x2 plus k square, or we can write 2hk del 2 upon del x del y. Then we will have k square del 2 f1 del y2. Then the third term will be 1 upon factorial 3 h cube del 3 upon del x3. Then we will have 3h square k del cube f upon del x square into del y. Then we will have 3hk square del cube f upon del x del y square. Then the next term will be k cube, then del cube f upon del y cube. So this is the expansion of Taylor series in case of variable 2. Now again if your x is, let us assume that h equal to x minus a and y equal to and k equal to y minus b. Let us assume that h equal to x minus a, or let x comma y is the point a comma b. Suppose that x is a and y is b, and h equal to x minus a and y equal to and k equal to y minus b. So if you put x equal to a and y equal to b here, then this will be a plus h. If we put x equal to a here, then this will be a plus h. Now as we are replacing h by x minus a, so this will be your f of x. So our f of x comma y will be f of a, your h was x minus a. So this is your del f upon del x at a comma b, then we have y minus b del f upon del y at a comma b. Then the second order term will be 1 by factorial 2 x minus a whole square del 2 upon del x2 at a comma b. Then we will have 2 times x minus a into y minus b into del 2 upon del x del y at a comma b. Then we will have y minus b whole square del 2 upon del y2 at a comma b, and then the third order derivatives. So this is the Taylor expansion of a function fxy in powers of x minus a and y minus b. Now if a equal to 0 and b equal to 0, then this Taylor expansion is known as Maclaurin expansion. Then Maclaurin expansion is given by your Maclaurin expansion will be f of xy equal to f of 0 comma 0 plus x del f upon del x at 0 0 plus y del f upon del y at 0 0. Then we will have the double order terms, x square your double derivative at 0 0. Then we will have 2xy del 2 upon del x del y at 0 0 plus y square del 2 upon del y2 at 0 0, and then the remaining terms. So this is known as the Maclaurin expansion of fxy at 0 0. So that means we can say that this is your Maclaurin series in ascending powers of x and y. Now let us solve questions based on these two expansion. So the first question is expand now the first question is expand e for x into cos y at say 1 comma pi by 4 point. That means when your a is 1 and b is pi by 4, then you have to expand this f of xy. So that means in this Taylor series we will put our a as 1 and b as pi by 4, and then we will solve it. So fxy solution, let your fxy is equal to e for x into cos y. So from here your del f upon del x will be. Now let us find out various derivatives, that means such as del f upon del x, del f upon del y, and then the second order derivatives. So your del f upon del x will be e for x cos y. Your del f upon del y will be e for x into the differentiation of cos y, which is your minus sin y, del 2f upon del x2, and this is your e for x cos y, del 2f upon del y2 minus e for x differentiation of cos y will be sin y, and then del 2f upon del x del y, the differentiation of this one with respect to x will be minus e for x into sin y. Now these values at 1 comma pi by 4 will be, now from here your 1 comma pi by 4 is, that means when your x is 1, and y is pi by 4, so that means this is your cos pi by 4, which is your 1 by root 2, so we will have e upon root 2, and from here your del f upon del x at 1 comma pi by 4 is again e upon root 2. From here our del f upon del y at 1 comma pi by 4 is minus e upon root 2. From here our del 2 f upon del x2 at 1 comma pi by 4 is equal to e upon root 2. So from here del 2 f upon del y2 at 1 comma pi by 4 is equal to minus e upon root 2, and from here del 2 f upon del x2 del x del y at 1 comma pi by 4 is minus e upon root 2. So let us put these values here in this Taylor expansion. So therefore our fxy is equal to, the first term was f a comma b. Your f a comma b is e by root 2. So we have e by root 2. Then x minus 1. The first term is x minus 1 into del f upon del x at 1 comma pi by 4, which is your e by root 2. Then we will have y minus b. B is pi by 4. Then the values of del f upon del y at 1 comma pi by 4 is minus e upon root 2. Then we will have 1 upon factorial 2, del square x minus 1 whole square into del into your the double derivative with respect to x, which is your e upon root 2. Then we will have 2 times x minus 1, y minus 1, y minus pi by 4, and the double derivative, this one, is e minus e upon root 2. Then we will have y minus pi by 4 whole square, and del 2f upon del y 2 is minus e by root 2. So this is our solution.